Right now, on the moon's south pole, something extraordinary is about to happen. Not in some distant sci-fi future, but within this decade. NASA isn't just planning another flag and footprints mission. They're building the foundation for humanity's first permanent settlement beyond Earth. And the way they're doing it will surprise you. Forget what you think you know about lunar bases. There are no inflatable domes being shipped from Earth, no instant cities. NASA learned the hard way that you can't just build a moon city the way you'd build on Earth. Apollo proved we could reach the moon, but it also proved that heroic one-off missions lead nowhere. Every landing reset the clock. Every success made the next attempt more expensive. That model is dead. So here's what's actually happening. NASA is building a city on the moon by not starting with buildings. They're starting with something far more fundamental, something that determines whether any permanent lunar structure can exist at all. And if you understand this one crucial decision, everything else about Artemis suddenly makes sense. The answer isn't about architecture or life support or radiation shielding. It's about supply chains. Specifically, how often can rockets fly? How reliably can cargo land? How much can humans actually build during their limited time in spacesuits? These aren't exciting questions, but they're the only questions that matter. Because permanence on the moon isn't built from habitats, it's built from logistics that never stop. The first mistake people make is assuming permanence is an architectural challenge. Domes, habitats, streets. NASA treats it as a logistics problem because every attempt to go beyond low Earth orbit has failed for the same underlying reason. You couldn't go back often enough. Apollo proved the moon was reachable. It also proved that without repetition, nothing lasts. Each mission discarded hardware, each landing reset the clock, and every success increased the cost of the next attempt. That model cannot support construction, maintenance, or growth. So the strategy changed. Artemis is not designed around a destination, but around cadence. How often launches can happen without starting from scratch each time. How reliably vehicles can land and leave. How much mass can be delivered repeatedly, not heroically. These constraints matter more than any single touchdown, because permanence only emerges when failure stops being fatal. A broken component becomes a delay instead of an abandonment. This is why the earliest milestones look deceptively modest. Uncrewed tests, orbital missions that never land, hardware validation that appears detached from surface life. But these steps aren't about the moon itself. They're about stabilizing the pipeline that reaches it. If that pipeline collapses, everything on the surface becomes stranded infrastructure. There's a dependency chain here that quietly governs every other decision, and it's worth slowing down to see how tight it really is. One constraint dominates the entire plan. People are light, construction is heavy. An astronaut plus life support weighs almost nothing compared to power systems, rovers, spare parts, shielding, and pressure vessels. If you can't land mass consistently, you can't build anything that survives its first failure. That's why NASA separated crew delivery from cargo delivery early on. Humans are not the bottleneck, tonnage is. That leads to a counterintuitive reality. Bigger rockets don't guarantee permanence. Frequency does. A system that flies once every few years, no matter how powerful, cannot support construction. Construction requires margin. Things break. Dust infiltrates. Components wear down. A settlement only works if replacement hardware is already scheduled to arrive. This is why repeatability quietly outranks spectacle. even when progress looks slow from the outside. Another subtle decision reshapes everything. Missions are no longer single arcs from Earth to surface. Lunar orbit becomes a buffer. Vehicles specialize. Some only move between Earth and orbit. Others only descend and ascend. That modularity lowers mission risk, but more importantly, it enables reuse. Reuse is the dividing line between exploration and infrastructure. When vehicles stop being disposable, missions stop being precious. Even with launches stabilized and cargo landing reliably, there's still a human bottleneck that caps everything immediately. It isn't radiation. It isn't power. It's time spent working outside. Apollo crews weren't limited by ambition. They were limited by endurance. Their suits allowed brief, exhausting work windows. Construction doesn't happen in bursts. It happens through hours of repetitive tasks, day after day. Without extending that window, surface systems accumulate faster than they can be assembled. This is why next-generation lunar suits are treated less like clothing and more like industrial equipment. Mobility determines how far materials can be moved. Dust resistance determines how long joints and seals survive. Thermal control determines whether crews can work through temperature swings instead of retreating from them. Increase productive hours per day and assembly timelines compress dramatically. Ignore it, and the surface fills with inert hardware waiting for attention. There's a mechanism tied to this we haven't broken down yet, and it quietly limits everything else. There's also a non-technical constraint shaping the sequence: political durability. Long programs survive by producing visible progress without catastrophic failure. Artemis is structured so each step stands independently. A test flight validates systems. An orbital mission validates crew operations. A landing validates surface access. If a later element slips, earlier successes remain intact. Surface infrastructure introduced too early would reverse that logic and concentrate risk instead of distributing it. So what looks like hesitation is actually sequencing. The absence of buildings isn't a delay, it's a filter. Only systems that survive repetition earn the right to stay. And once that repetition exists, every additional day on the surface stops being an experiment and starts becoming something else entirely. Something that behaves less like exploration and more like work. Once transport stops being the primary limiter, the problem shifts immediately from movement to endurance. Not survival in the abstract, but duration under real working conditions. Apollo missions proved humans could operate on the moon. They also proved that without systems designed for time, every task becomes a race against exhaustion, temperature, and exposure. Staying longer doesn't just stretch missions, it forces an entirely different way of designing everything on the surface. This is why location matters more than architecture. NASA's focus on the lunar South Pole isn't aesthetic or symbolic, it's mechanical. Certain ridge lines there receive sunlight for most of the lunar year, while nearby craters remain permanently shadowed. That combination quietly solves two problems at once. Sunlight simplifies power generation. Shadow preserves water ice. Together, they define where humans can stay without dragging Earth behind them. Power becomes the first survival system that starts behaving like infrastructure. Short missions can rely on batteries and carefully timed operations. Long missions cannot. The 2-week lunar night is unforgiving, and no amount of scheduling fixes the absence of energy. That's why surface power is treated as a continuous requirement rather than a consumable. Once power becomes steady instead of rationed, everything else stretches with it. Habitat climate control, tool usage, communications, even crew psychology. Habitats themselves are designed around this logic. Early structures are not meant to impress. They are meant to disappear into the environment. Smaller volumes are easier to pressurize, easier to shield, easier to repair. Radiation exposure isn't managed through medicine or short stays. It's managed through geometry and placement. Put mass between humans and space, and cumulative risk drops. This is why surface living initially looks compressed, layered, and deliberately unromantic. Life support follows the same trajectory. On short missions, air and water are supplies. On long missions, they are loops. Recycling isn't a convenience, it's a prerequisite. Systems derived from orbital experience are redesigned to tolerate dust, gravity, and intermittent maintenance. The moment resupply stops being frequent, waste stops being waste and starts being raw material. That shift doesn't feel dramatic, but it fundamentally changes how long crews can remain without external intervention. Radiation is often framed as the ultimate barrier, but time changes how it's handled. Short exposure is managed through mission limits. Long exposure is managed through structure. Shielding isn't optimized for comfort. It's optimized for cumulative dose reduction. That means walls, regolith coverage, and positioning matter more than personal protection. Over months, small reductions add up to meaningful differences in lifetime risk. And that math quietly governs how surface layouts evolve. Pressurized rovers become part of this endurance strategy. They aren't vehicles in the traditional sense. They're extensions of the habitat. Multi-day excursions stop being emergencies and start becoming planned operations. Distance increases not because humans become tougher, but because environments become continuous. When shelter travels with the crew, the moon stops being a series of isolated safe points and starts behaving like a connected workspace. What emerges here is a subtle transition. Systems originally justified as survival tools begin enabling productivity. Power supports tools instead of just lights. Habitats support planning instead of recovery. Rovers support logistics instead of exploration. None of this is framed as a settlement yet, but the behavior starts to change. Days become predictable. Tasks become routine. Maintenance replaces improvisation. The critical realization is that endurance exposes inefficiency. The longer crews stay, the more obvious it becomes which systems are draining time instead of saving it. Manual setup becomes a liability. Repetitive tasks demand automation. Every hour spent maintaining life support is an hour not spent assembling anything new. This pressure doesn't come from ambition. It comes from arithmetic. As duration increases, human presence stops being the dominant factor. Machines begin to take over, not because they're more capable, but because they scale without fatigue. The surface starts to favor systems that can run continuously, unattended, and redundantly. Humans shift towards supervision, repair, and decision-making. That transition doesn't announce itself, but once it starts, it accelerates. At that point, survival systems are no longer just keeping people alive. They are defining how work gets done, how resources are allocated, and how long anything can remain functional without replacement. Time stops being the enemy it was during short missions. It becomes the variable everything else is optimized around. Once endurance stops being the dominant constraint, the moon stops behaving like a hostile destination and starts behaving like a system that can be optimized. This is the point where supplying the surface from Earth becomes the most inefficient option available. Every kilogram launched uphill from a gravity well competes against a simpler question: what can be sourced locally instead? Water is the first lever that changes everything. Not because it's rare, but because it's flexible. In one form, it keeps crews alive. In another, it becomes oxygen. Split further, it becomes fuel. Even before extraction reaches industrial scale, the presence of usable water rewrites mission math. Mass that once had to be launched repeatedly becomes a one-time investment. Logistics chains shorten, safety margins widen. The surface begins to feed itself, even if only partially. The same logic applies to material. Lunar soil is not dirt in the terrestrial sense, but it is abundant, predictable, and already where it needs to be. When landing pads, roads, and shielding can be fabricated in place, the environment stops damaging infrastructure faster than it can be repaired. Dust becomes something to manage instead of something to flee from. Construction shifts from delivery to assembly, and that shift removes an entire class of risk. This is where robotic systems stop being precursors and start becoming the backbone. Machines don't replace humans because humans are incapable. They replace them because repetition is expensive when done by people. Robots can grade surfaces, sinter material, and maintain power systems continuously. Humans arrive to correct, upgrade, and adapt. The workload inverts. Presence becomes strategic instead of constant. As this balance shifts, the surface begins to resemble an ecosystem rather than an outpost. Power feeds machines. Machines prepare terrain. Prepared terrain reduces wear. Reduced wear extends system lifetimes. Longer lifetimes reduce replacement demand. Each improvement compounds. None of it requires a declaration of permanence. It emerges from efficiency. At this stage, the definition of independence becomes narrower and more precise. Full autonomy isn't required. What matters is reducing the rate at which Earth must intervene. If surface operations can survive delays, missed launches, or political pauses without collapsing, they stop being fragile. Fragility is what kills long-term projects, not technical difficulty. Governance quietly enters here, not as ideology, but as scheduling. When assets persist, they need coordination. When resources are shared, they need allocation. When multiple actors operate in the same environment, behavior becomes policy, whether it's labeled that way or not. A city isn't declared, it's administered. The paperwork follows the plumbing. The most important transition isn't visible from orbit. It happens when surface activity no longer clusters around arrival dates. When work continues whether a crew has just landed or not. When absence doesn't mean abandonment. That's the moment the moon stops being visited and starts being used. What's striking is how uncinematic this transformation is. No ribbon cutting, no skyline, just fewer emergencies, fewer single points of failure, and fewer reasons to rush. Stability replaces urgency. Planning horizons stretch from missions to years. The systems don't feel alive, but they behave as if they expect to remain. And once that expectation exists, expansion stops being aspirational. Additional habitats justify themselves. Extra power capacity makes sense. Redundancy becomes cheap instead of wasteful. Growth isn't driven by optimism, it's driven by accounting. The surface supports more activity because it already supports some. This is where the word city becomes misleading. Cities are not defined by population or buildings. They're defined by persistence, by systems that outlast individual occupants, by infrastructure that assumes continuity. On the moon, that continuity doesn't begin with people deciding to stay. It begins with systems that make leaving unnecessary. None of this requires a leap of faith. It requires sequencing. Transport first, endurance second, local sourcing third. Each step constrains the next until options collapse into a narrow path. The path isn't glamorous, but it's durable. And durability is the only currency permanence ever accepts. So here's the question I want you thinking about. Once a place can power itself, repair itself, and resupply itself, at what point does choosing not to live there become the more radical decision? If you're fascinated by the moon and want to dive even deeper, check out on the end screen our video 50 Amazing Facts About the Moon, where we explore the most mind-blowing lunar discoveries and mysteries.